The problem of stopping, often referred to as the optimal stopping problem, is a fundamental concept in probability theory and mathematical optimization. It involves determining the best time to take a particular action to maximize an expected reward or minimize an expected cost. This problem appears in various fields such as statistics, economics, and finance. Let's break down the key points. 1. The definition and basic concept. The optimal stopping problem can be described as follows. Objective: choose a time to stop a process to achieve the best possible outcome. Process: this involves observing a sequence of random variables over time. Reward function: at each time step, there is an associated reward or cost, which depends on the observed values of the random variables. 2. Discrete time case. In the discrete time case, the problem is often formulated with a sequence of random variables, x_1, x_2, that's, x_n, and a sequence of reward functions, y_1, y_2, that's, y_n. The goal is to choose a stopping time, /τ, a specific time step, to maximize the expected reward, /math, y_\tau. 3. Continuous time case. In continuous time, the problem involves a gain process, g_t, defined on a filtered probability space. The objective is to find a stopping time, /τ, that maximizes the expected gain. Vt equals τ greater than or equal to ZP, g, where Vt is called the value function. 4. Solution methods. There are several methods to solve optimal stopping problems. Dynamic programming. This method involves breaking down the problem into simpler subproblems and solving them recursively. It is particularly useful in discrete time cases with a finite planning horizon. Martingale approach. This approach uses martingale theory, focusing on the Snell envelope, which represents the optimal stopping rule. Markov method. When the underlying process is a Markov process, powerful analytical tools from the theory of Markov processes can be utilized. 5. Applications. Optimal stopping problems have numerous applications. Finance, in the pricing of American options, where the holder can choose the optimal time to exercise the option. Statistics, in sequential analysis, where decisions are made based on ongoing observations, such as clinical trials. Economics, in decision-making processes where timing is crucial, such as investment decisions. 6. Example secretary problem, a classic example where the goal is to choose the best candidate from a sequence of applicants by stopping at the right time. American options, in financial markets, determining the optimal time to exercise an option to maximize profit. 7. Challenges complexity. The problem can become highly complex, especially in continuous time with infinite horizons. Uncertainty. The randomness in the process adds a layer of uncertainty, making it challenging to determine the optimal stopping time. In summary, the optimal stopping problem is a rich and versatile concept with wide-ranging applications. It involves choosing the best time to take an action based on observed data to maximize rewards or minimize costs. The problem can be approached using various mathematical techniques, each suited to different types of processes and applications assumptions about the process. Markov property. Many solutions assume the underlying process has the Markov property, meaning the future state depends only on the current state and not on the past states. This simplifies the problem but may not always be realistic. Stationarity. Some models assume that the statistical properties of the process do not change over time. In reality, many processes are non-stationary, with changing dynamics. 2. Information and observability. Perfect information. Optimal stopping problems often assume that the decision maker has perfect information about the process and the rewards. In practice, there may be incomplete or noisy information. Observability. It is assumed that the decision maker can observe the process continuously or at discrete intervals without any delay. However, in real-world scenarios, there might be observation lags. 3. Reward structure. Known reward function. The reward function is typically assumed to be known and well-defined. In many practical situations, the reward structure might be uncertain or difficult to quantify accurately. Fixed horizon. Some problems assume a fixed time horizon within which the decision must be made. This may not always align with real-world scenarios where the horizon can be uncertain or flexible. 4. Mathematical complexity. Analytical solutions. Finding analytical solutions can be challenging, especially for complex processes or in continuous time. This often necessitates numerical methods, which can be computationally intensive. High dimensionality. In problems with multiple variables or dimensions, the complexity increases significantly, making it harder to find optimal solutions. 5. Practical implementation. Computational resources, solving optimal stopping problems, especially in high-dimensional or continuous time settings, can require significant computational resources. Robustness, solutions may be sensitive to model parameters and assumptions. Small changes in the underlying assumptions can lead to different optimal stopping rules. 6. Real-world constraints. Regulatory and operational constraints. In practical applications, there may be regulatory, operational, or logistical constraints that are not accounted for in the theoretical models. Human factors. Decision-making in real-world scenarios often involves human judgment, which can introduce biases and deviations from the optimal stopping rule. 7. Examples of limitations. Secretary problem assumes a known number of candidates and that each candidate can be ranked perfectly. In reality, the number of candidates might be unknown, and rankings can be subjective. American options assumes continuous monitoring of the option's value and the ability to exercise at any time. In practice, there might be restrictions on exercise times and transaction costs. Understanding these limitations and assumptions is crucial for applying optimal stopping theory effectively in real-world scenarios. It helps in identifying potential gaps and areas where the model might need adjustments or additional considerations. The Markov property is a fundamental concept in probability theory and statistics, describing a specific characteristic of certain stochastic processes. Definition: the Markov property states that the future state of a stochastic process depends only on the present state and not on the sequence of events that preceded it. In other words, given the present state, the future states are independent of the past states. This is often referred to as the memoryless property. Formal definition: for a stochastic process, x_t, with a state space, S, the Markov property can be formally expressed as P xt plus 1 equals xt plus 1 xt equals xt, xt1 equals xt1, x0 equals x0, tongue poking smiley, xt plus 1 equals xt plus 1 xt equals xt. This means that the conditional probability of the next state, x_t plus 1, given the current state, x_t, is the same as the conditional probability given the entire history of states. Examples: Markov chains. In discrete time Markov chains, the process moves between states in a state space according to transition probabilities that depend only on the current state. Brownian motion. In continuous time processes like Brownian motion, the future position of a particle depends only on its current position, not on the path it took to get there. Applications: the Markov property is widely used in various fields: finance, modeling stock prices and other financial instruments. Queuing theory, analyzing systems like customer service lines where the next state depends only on the current number of customers. Genetics, studying the inheritance of traits where the future genetic state depends only on the current state. Importance: the Markov property simplifies the analysis and prediction of stochastic processes by reducing the dependency on historical data. This makes it easier to model and compute probabilities and expected values for future states. Limitations: while the Markov property is powerful, it assumes that the process is memoryless, which may not always be realistic. Some processes have dependencies that extend beyond the current state, requiring more complex models. In summary, the Markov property is a key concept that helps in understanding and modeling processes where the future is independent of the past, given the present. Non-Markovian processes. Memory effects. Some processes have memory, meaning the future state depends on more than just the current state. For example, in autoregressive models of order greater than 1, RP models, the future state depends on multiple past states. Path dependency. In certain financial models, the value of an option might depend on the entire path of the underlying asset's price, not just its current price. 2. Hidden Markov models, HUM. Hidden states. In HUMs, the observed process does not have the Markov property, but the underlying hidden states do. This adds complexity because the observed data does not directly follow the Markov property. 3. Time-varying transition probabilities. Non-stationarity. If the transition probabilities change over time, the process may not satisfy the Markov property. For example, in seasonal models, the transition probabilities might vary with seasons or other time-dependent factors. 4. External influences. Exogenous factors, external factors or shocks that influence the process can violate the Markov property. For instance, sudden economic events can affect financial markets in ways that are not captured by a Markov model. 5. Complex dependencies. Higher-order dependencies. Some processes have dependencies that extend beyond the immediate past state. For example, in biological systems, the future state of a cell might depend on a sequence of past states due to complex biochemical interactions. 6. Practical limitations. Data limitations. In practice, the assumption of the Markov property might not hold due to limitations in data quality or availability. Noise and measurement errors can also affect the validity of the Markov assumption. Examples of exceptions. Weather prediction. Weather systems often exhibit dependencies that extend beyond the current state, influenced by various atmospheric conditions over time. Human behavior. In modeling human behavior, past experiences and long-term memory can play significant roles, making the Markov property an oversimplification. Summary. While the Markov property simplifies modeling and analysis, it is important to recognize its limitations and the contexts in which it may not apply. Understanding these exceptions helps in choosing the appropriate models and methods for different types of processes. Model selection and complexity. Choosing the right model. When the Markov property does not hold, it is crucial to select models that can capture the dependencies and memory effects. For example, using autoregressive models, RP, or hidden Markov models, HUMs, can better represent processes with memory. Increased complexity. Models that account for non-Markovian behavior are often more complex and computationally intensive. This can impact the feasibility of real-time decision-making and require more sophisticated algorithms and computational resources. 2. Data requirements. Historical data. Non-Markovian models typically require more historical data to accurately capture the dependencies. This means that decision-makers need access to comprehensive datasets, which can be challenging to obtain and manage. Data quality. High-quality data is essential to accurately model the dependencies. Noise and errors in the data can significantly affect the performance of the model. 3. Predictive accuracy. Improved predictions. By accounting for memory and path dependencies, models can provide more accurate predictions. This is particularly important in fields like finance, weather forecasting, and healthcare, where accurate predictions can lead to better decision-making. Uncertainty management. Understanding the limitations of the Markov property helps in managing uncertainty and risk. Decision-makers can develop strategies that are robust to the complexities and uncertainties inherent in the process. 4. Real-world applications. Finance. In financial markets, models that account for historical price movements and external shocks can better predict asset prices and inform trading strategies. For example, using models that incorporate volatility clustering and long-term dependencies can improve risk management. Healthcare. In medical decision-making, considering the patient's medical history and long-term health trends can lead to better treatment plans. Models that account for these factors can improve the accuracy of diagnoses and treatment outcomes. Supply chain management. In logistics and supply chain management, understanding the dependencies between different stages of the supply chain can help in optimizing inventory levels and reducing delays. 5. Operational challenges. Implementation complexity. Implementing non-Markovian models can be challenging due to their complexity. Organizations need skilled personnel and advanced tools to develop, validate, and maintain these models. Scalability. As the complexity of the model increases, scalability becomes an issue. Decision-makers need to ensure that the models can handle large-scale data and provide timely insights. 6. Strategic planning. Long-term planning. Non-Markovian models are better suited for long-term planning as they can capture trends and patterns over extended periods. This is useful for strategic decision-making in areas like urban planning, environmental management, and policy development. Adaptive strategies. Understanding the limitations of the Markov property encourages the development of adaptive strategies that can respond to changing conditions and new information. Summary. Recognizing the exceptions to the Markov property and their implications helps in selecting appropriate models, improving predictive accuracy, and making informed decisions. It also highlights the importance of high-quality data, computational resources, and skilled personnel in managing complex processes. One real-world scenario where non-Markovian behavior significantly impacts outcomes is in financial market modeling, particularly in the context of stock price movements and option pricing. Example: financial markets and stock prices. Context: in financial markets, the prices of stocks and other assets often exhibit complex behaviors that cannot be fully captured by models assuming the Markov property. Traditional models like the geometric Brownian motion (GBM) assume that stock prices follow a Markov process, where future prices depend only on the current price and not on the past prices. Non-Markovian behavior. However, empirical evidence shows that stock prices often exhibit volatility clustering and long-range dependence. Volatility clustering. Periods of high volatility tend to be followed by high volatility, and periods of low volatility tend to be followed by low volatility. This indicates that the future volatility of a stock is influenced by its past volatility, violating the Markov property. Long-range dependence. Stock returns can exhibit correlations over long periods, meaning that past returns can influence future returns over extended time horizons. Practical implications. Option pricing. The pricing of financial derivatives, such as options, is significantly impacted by non-Markovian behavior. Models like the Black-Scholes model assume constant volatility and Markovian price movements. However, in reality, the volatility is stochastic and exhibits clustering. This leads to the development of more sophisticated models like the Heston model and GARC, generalized autoregressive conditional heteroscedasticity models, which account for changing volatility over time. Risk management. Accurate risk assessment requires models that capture the true behavior of asset prices. Non-Markovian models provide better estimates of risk measures like value at risk, VaR, and expected shortfall, S, by considering the persistence in volatility and returns. Investment strategies. Portfolio managers and traders use models that account for non-Markovian behavior to develop more effective trading strategies. For example, momentum trading strategies exploit the persistence in stock returns, while mean reversion strategies take advantage of the tendency of prices to revert to their historical mean. Conclusion. In summary, non-Markovian behavior in financial markets necessitates the use of more complex models that can capture the dependencies and memory effects in stock prices. This leads to more accurate pricing of financial instruments, better risk management, and more effective investment strategies. The Heston model is a widely used stochastic volatility model in financial mathematics, particularly for pricing options. It was developed by Stephen Heston in 1993 and addresses some of the limitations of the Black-Scholes model by allowing for stochastic, random volatility. Key features of the Heston model. Stochastic volatility. Unlike the Black-Scholes model, which assumes constant volatility, the Heston model assumes that volatility itself follows a random process. This allows the model to capture the observed market phenomenon where volatility changes over time. Mean reversion. The model incorporates mean reversion in volatility, meaning that volatility tends to revert to a long-term average over time. This is more realistic as it reflects the tendency of market volatility to fluctuate around a historical average. Correlation between asset price and volatility. The Heston model allows for a correlation between the asset price and its volatility. This is important because in reality, asset prices and their volatilities are often correlated. Mathematical formulation. The Heston model is defined by the following set of stochastic differential equations, SDE's asset price dynamics. DST equals STDT plus VTSTDWTS, where S_T is the asset price at time, T. \mu is the drift rate, expected return. V_T is the instantaneous variance, volatility squared, at time, T. W_T_S is a Wiener process, standard Brownian motion, for the asset price. Variance dynamics. dVt equals kappa, theta vt, dt plus vt dwtv, where V_T is the instantaneous variance at time, t. \kappa is the rate of mean reversion. \theta is the long-term average variance. \11 is the volatility of volatility, vol. W_T_V is a Wiener process for the variance. \rho is the correlation between W_T_S and W_T_V. Parameters of the Heston model. The model has 5 key parameters: \nu_0 initial variance, \theta long-term average variance, \kappa rate at which variance reverts to the mean, \11 volatility of volatility, \rho correlation between the asset price and its volatility. Applications. Option pricing. The Heston model is primarily used for pricing European options. It provides a closed-form solution for the price of European call and put options, making it computationally efficient. Risk management. By modeling stochastic volatility, the Heston model helps in better assessing and managing financial risks. Volatility smile. The model can capture the volatility smile observed in the market, where implied volatility varies with strike price and maturity. Advantages. Realistic volatility modeling captures the dynamic nature of market volatility. Mean reversion reflects the tendency of volatility to revert to a long-term average. Correlation accounts for the correlation between asset prices and volatility. Limitations. Complexity. The model is mathematically more complex than the Black-Scholes model. Parameter estimation. Estimating the parameters accurately can be challenging and require sophisticated techniques. Summary: the Heston model is a powerful tool for option pricing and risk management, offering a more realistic representation of market dynamics by incorporating stochastic volatility, mean reversion, and correlation between asset prices and volatility. The optimal stopping problem has a rich history in mathematics and has evolved significantly over time. Here's a detailed explanation of its origins and development. 1. Early beginnings. The concept of optimal stopping can be traced back to problems in gambling and decision theory. One of the earliest known problems related to optimal stopping is the St. Petersburg paradox, formulated by Daniel Bernoulli in 1738. This paradox highlighted the need for a rational decision-making framework under uncertainty. 2. Formalization in the 20th century. The formal study of optimal stopping problems began in the mid-20th century. Key developments include Wald's sequential analysis. 1940s Abraham Wald introduced sequential analysis, which involves making decisions based on sequentially observed data. This laid the groundwork for optimal stopping theory by addressing when to stop an experiment to make a decision. Bellman's dynamic programming. 1950s Richard Bellman developed dynamic programming, a method for solving complex problems by breaking them down into simpler subproblems. This approach is fundamental to solving optimal stopping problems, as it allows for the recursive computation of the optimal stopping rule. 3. The secretary problem. 1960s. One of the most famous optimal stopping problems is the secretary problem, also known as the marriage problem. It was popularized in the 1960s through a Scientific American article and further analyzed by mathematicians like Dynkin. The problem involves interviewing a sequence of candidates and deciding when to stop and hire the best candidate seen so far. The solution involves a specific stopping rule that maximizes the probability of selecting the best candidate. 1. 4. Mathematical formalization. The theory of optimal stopping was further formalized through the work of mathematicians such as John von Neumann and Oscar Morgenstern. Their work on game theory in the 1940s provided a foundation for decision-making under uncertainty. Dynkin and Yukevic, 1969. They published a comprehensive study on controlled Markov processes, which included optimal stopping problems. 5. Applications in finance. 1970s and beyond. The 1970s saw the application of optimal stopping theory in financial mathematics, particularly in the pricing of American options. An American option can be exercised at any time before expiration, making it an optimal stopping problem. The development of models like the Black-Scholes model and later the Heston model incorporated optimal stopping rules to determine the best time to exercise options. 2. 6. Modern developments. Today, optimal stopping problems are studied in various fields, including statistics, sequential hypothesis testing, and change point detection, economics, investment decisions and real options analysis, operations research, inventory management and queuing theory, artificial intelligence, reinforcement learning and decision-making algorithms. Summary: the optimal stopping problem has evolved from early gambling problems to a well-established field in mathematics and applied sciences. Its development has been driven by contributions from various disciplines, leading to a wide range of applications in finance, economics, statistics, and beyond. That was all. Goodbye.